Okay, we shall start our class. So in this chapter, we will learn about the audio compressions. Uh, the flow that we are going to learn audio compression is same as the image compressions, where we will explore the limitation of human ear or the auditory system instead of the eye. Okay, so I think we start at PCM. Yeah. So PCM, as I mentioned previously, all the sound wave that we receive from the nature environment is in analog. Okay, so analog sound wave we are going to convert to digital because when we want to process anything, especially in multimedia everything is in digital. So if you want to process anything, you have to convert the original or analog waveform to digital, which is so-called the discrete waveform. So these conversions later on in computer science will be, the code to become 1 and 0 to become a bit stream over there. Okay, so this process is known as PCM, pulse code modulation. Analog input signal information is converted to binary code. So the output of the PCM will be a binary. So this will be your input and this will be your output. And this process convert from input to output is called PCM. So you have a partition into three columns. The first one, sampling, quantizing, and also encoding. So for the first one, you have to sample at twice, which obey the Nyquist theorem, and then round off the sample to one of the 256 level, and then encode it to become 1 and 0. So sampling, as I mentioned before, sampling is in terms of time domain, and quantization is against the frequency or the amplitude. Okay, so the y-axis is always about, in audio, y-axis is always about the uh, loudness, the intensity of a specific sound wave and or audio wave, etc. And for the x-axis, usually we will put it as the time domain. If let's say you want to interchange the x and y axis, it's okay as well. Just that your graph would be maybe to this side okay. So sampling is always about the time domain. So it is about the periodic measurements of the analog signal and change in its continuous time signal into discrete time signal. Continuous time signal change to discrete time signal is actually yeah, ADC okay, analog to digital converter. So after sampling, the signal value is known only at the discrete point at a time, called sampling instant. Therefore, continuous time signal curve can be described by the sample value. So this is why we need the Nyquist theorem. If we did not obey the Nyquist theorem, basically after you sample and change the entire continuous waveform into sample instant, you will not able to mimic or approximate the original analog waveform. So that condition we don't need as either under sampling or aliasing. We don't have over sampling in this condition because uh, nothing is over okay. Because if you are over sampling, which means you have a lot of different many different instant to describe analog waveform. That one is just to in overall will increase the data size only, but did not at least it will reflect the original waveform okay. So sample value, the value of the function at the sample point. This is regarding the amplitude at the y-axis. Sampling interval will always fix. Okay, if you have 1 second, if you want to partition into four, you take four sample, so for sure the interval will be the same. Okay, this is not a good chart Okay, so you have what I want to imply is that the interval is the same Okay, if a signal is slowly varying, then fewer sample per second will be required than if the waveform is rapidly varying. What is mean by here is that if you have a waveform that you change in the pattern in require a very big transition or very huge transition period to change to a specific level. So for this kind of waveform, you don't really need to take a lot of sample per time. Okay, for example, let's say you have your something like this, change very, very slowly. You can actually take one sample, one sample, one sample, one sample, one sample, but still can describe the original waveform. For example, after you're taking this one, remove the original one, you'll still be able to reflect the original waveform. Okay, but let's say if you have another waveform which is changed rapidly, so you only remain this sampling data, you will not able to represent the original sample. Okay, so this is what it means. But of course, not all the time you will able to know what would be the types or be the modes of the or input signal. Okay, so we would expect to take input for sure like if you already know your application is the input waveform is always very slow in transition, so you can reduce your sampling size since you already know that uh, the changes will not be something like that based on empirical analysis, of course. So the optimal sampling rate or sampling frequency depends on the maximum frequency component present at the in the signal. So this is the sampling instant, which means sampling instant is actually the instant where you take a sample. So all these dotted line are samplings instant. So after that, you will get sort of this one sample signal. The waveform would be removed because waveform is not the one that you want, but you want to sample it, and this is what you want. Quantizing is always in the y-axis. Each accurate sample value is round off to the closest numerical value in a given numerical set. In quantizing process, the information in accurate signal value is lost because the of rounding off an original signal cannot be reproduced exactly anymore. So this is what we call approximations, because as you approximate the analog signal, for sure you will have rounding off issue. For example, if you take something like this one, so you have, I mean, maybe 0 point something or maybe 1 something greater than the original analog. And for this one, perhaps you have a value lesser than the original analog. Okay, so and when we have value, for example, with a floating point at 0.042, something like that, or 0.099, so you would round off to become 0.1, or maybe you have 1.7 round off to become 2, something like that. All this rounding off, actually you're introducing noise to your system. Just that how severe is the noise. If this is what we so-called the signal to quantization noise. So if the noise is sufficient, I mean, if the noise is very significant, you might be the noise might interfere your original input audio. But nonetheless, always remember for quantization noise, this would be the maximum noise level. That is because the quantization noise will always happen around this region. Okay, for the region around here will not happen quantization issue, because quantization is only happen in a small frequency. So at most kept as 6.02 multiplied by number of bit. So if let's say you have number of bit 8 bit, so perhaps 6.02 multiplied by 8 lah, that's all. Okay. More quantization step can be used for better performance. More quantization step is that you increase the sensitivity in terms of y-axis, which means you increase more and more sensitive. But of course, if you increase the sensitivity, you increase the data size as well. Okay, because you're taking more sample. So the difference between the quantized amplitude and actual signal amplitude is called quantization error. Okay, and you can actually calculate using SQNR, signal to quantization noise ratio. The more the quantization step of fine quantization, the lower the quantization error. So that is why if you have a very coarse y exit, so your quantization error will be increased. But if you have a very sensitive quantization, so your quantization error will be decreased, but your data size will increase. Okay. So encoding and coding. The coding process will convert discrete amplitude signal into a series of binary bits for transmission and storage. For example, the amplitude space referred to the figure next page, this one, is evenly divided into 6 different quantization steps. The 3-bit binary code can be used. Each quantized amplitude is coded into binary bit. So for this one, I mean, we will go until this level only lah. I mean, in depth how to convert the the entire PCM process until you get the binary code 1 and 0. We are not that is beyond our syllabus. So this is just to let you know. For example, you have the values sample here, sample here, sample here. So you will be able to take this value as your binary bit lah. Okay, which means that you have value here, you will get 100 as your binary bit, something like that. Okay. So those that did not hit, for example, this one, you are not achieving 3 yet, so you will drop down to become 2. Okay, unless you have a sensitive value. I mean, more sensitive value. For example, you have something like this is 3, this is 4 lah. Okay, for example, this is 1xx lah, whatever. So you will get the value here exactly. So since you have now you have this y exit and your value is here, so you will get the value of this one for this specific value because you yet to hit 3, right? So you have to you are in the middle between 2 and 3, so you will back to 2 lah. Okay, so this gap would introduce quantization error, quantization error. Okay, so that is the reason why we need uh, better sensitivity in terms of quantization, so that the noise introduced will be lower. Okay, so perception, audio compression, and psychoacoustic. Uh, perception is perceptual is that we uh, human perceptual lah. For example, when we go to sort of concert, and after that we receive emergency call, and then we come out from the concert and you try to answer the phone call, and you literally can't hear what your friend is talking about because the the ambient noise from the concert is very loud. So you already familiar with that frequency or that loudness of noise, and then once someone beside you whisper to you, definitely you cannot hear that. I think everyone been experienced such a conditions that, or maybe a bomb happened very near to you, you might suffer from humming, and that humming is very annoying. And at the same time, anyone talk to you, I don't think you will able to listen what he or she is talking lah. Okay, so why is such a condition happen is that we have a greater loudness or frequency happen, and then all this noise or all this audio is still present over there, but it's being masked out. So basically, you have a huge noise, and then this would be the masking area. Of course, this masking area will be various, depends on people, but there must be a sort of masking area. For some people that is more not so sensitive, perhaps the masking area will be greater. If those people that can recover or resilient enough, the masking area will be smaller, something like that. So if let's say there is a huge sound happen here, and then later on someone whisper to you, and the sound intensity is lower than this masking area, so this sound will not be able to hear or being able to perceive by the human. Okay, so if let's say you have you know wow, very loud music, okay, but suddenly a bomb happened, so this music will be masked out, something like that. Okay, so this is the we are exploring the human perception in such a way. So if let's say in during the audio compression, if we found that, oh, there is a very significance or very high amplitude of a frequency or noise. So all this area we would expect not being perceived by human being. So this would be the data that we're going to omit. Okay, we are going to omit all this data because eventually this data presence uh, in the multimedia itself, the human being it will not be able to listen that sound or whatsoever noise and etc. So all this data would be seen as redundancy lah. So will be omitted. Okay. The another thing is that we in the previous lecture, in the previous chapter, we learned about. I mean, human do have a specific range of audibility, right? So beyond that, and I mean lower than the lower than the auditory system and higher than the frequency that human being can perceive, we will still remove all those value because all those value is considered as redundancy. Eventually present, you will not able to listen. Okay, so this is so-called the perceptual audio compressions because all these are based on human being. Okay, if let's say the core person who use the multimedia or interact with the multimedia is not human, then this perceptual audio might not be applicable anymore. Okay. Okay, the impact as I mentioned in previous slide, is a expert group lah, which is more likely on the moving picture. Okay, JPEG is on static picture. So impact audio algorithm compress. Although impact is a group of people, but in this term, impact is actually referring to audio compression algorithms. Uh, just like the JPEG. JPEG is actually a group of people, and at the same time, if you mention JPEG in image processing, it is referring to the compression of image. Okay. So MPEG or the audio algorithm compress the audio data in large file by removing the acoustically irrelevant parts of the audio signal. That is, it takes advantage of the human auditory system inability to hear quantization noise under condition of auditory masking. So such an event that I described here, oh, I cannot listen to those whisper after I exit from the concert hall and etc. This condition or this phenomena we known as auditory masking. Okay, we known as this as masking, but auditory masking. So this masking perceptual property of the human auditory system that occur whenever the presence of a strong audio signal. Strong audio signal make a temporal or spectral neighborhood of weaker audio signal imperceptible. Temporal or spectral is that, as I mentioned previously, temporal is always referring to time, I mean space or time. So this statement means that if you have one, two, three, four, this is second. So if let's say you have a very strong audio here, so the adjacent audio would be masked up. Okay, but of course, if you have another stronger audio, that one will be able to perceive. Okay, so this is what it means by here. So empirical result shows that human auditory system has a limit, which is around 20 to 20 kilohertz frequency dependent solution resolution. Empirical result is the Fletcher Munson graph or curve. I will mention later on. Okay, that is the empirical result. Empirical result is a very tricky word because uh, empirical is something that uh, I'm not sure, but I asked a group of people come and test, come and testify, and come up with this kind of result. For example, I'm not sure what is the lifespan of human in for Malaysia citizens. So I'm not sure. I don't have the data. So I open up as question A. Not question A like you impossible to survey for dead people. So you find the this is not a good example. Okay, I'm not sure. I mean, I'm not sure what is the mm, favorite food in Malaysia. So I will ask people from Thai UC, ask people from UTM, from Unimap, from USM, and etc., and maybe some other people. So I tabulate out a table. So that would be the so-called empirical analysis. You did not based on any fundamental theory, but you study a group of people, and this is what is the result. This is so-called empirical analysis. Uh, Sometimes you can use this word empirical for try and error, but try and error is really not a good word. Try to avoid in your thesis, in your uh, technical writing. Try to avoid this one. Sometimes people using the word empirical or heuristic. Heuristic. Heuristic is something similar to empirical as well. So we call select heuristically. For example, thresholding, right? So we don't really say that, for sure people will know thresholding must set one by one, right? So, but especially for those that are using doing image processing as your final year project, try not to use the word test and try and error. This is not a good word, but you can say heuristically. Heuristically, which means you study a specific group of image and you found that this threshold value is better. So we say that the selected threshold value is 100, bracket selected heuristically, something like that. Else, you can provide your data. Oh, after I study how many images, this would be the value this would be the optimized value that I have, something like that. Okay, so this is the way that we justify in terms of engineering. Okay, but nonetheless, I wouldn't say this is a strong justification. Okay, but it is acceptable. Okay, so the Fletcher Munson's chart is same as this one. Basically, the mathematician invite a group of people, of course, a lot of people, and then they play them different audio with different frequency, and then they collect the data. Oh, and found that people are, I mean, the human auditory system is more sensitive in this range, 20 to 20 kilohertz. Okay, so the dependency can be expressed in terms of critical band width that are less than 100 hertz for the lowest audible frequency and more than 4 hertz at the highest at the highest. So the human auditory system blurs the various signal component within the critical band, although this system frequency selectivity is much finer than a critical band. Critical band is actually a band that you're able to listen. For example, critical band don't have any specific frequency or specific resolutions. For example, now I speak, I giving lecture in front and you all can listen. This is the critical band for you all to listen. So if let's say you have another noise from the construction area and that construction area is huge enough to interfere to interfere my voice. So actually this is defining that both the my voice and the noise from the construction area is in the same critical band. So if let's say this the second noise is larger than mine one, it is going to mask my voice. Okay. If let's say now I speak, you can listen, but perhaps there would be some other maybe bees flying around which is very far from you and you cannot hear the sound from their wings. So that one is another critical band. Those that you cannot perceive is not the critical band that is belong to the area that you can listen. Do you understand? Okay. So which means if let's say you now in this critical band, so if let's say another noise, maybe from the bell, trying to interfere. So let me use another color, trying to interfere at this region. So, and if this noise from the bell is high enough, it will tend to mask up this region. But why this region is not masking out? Because this region is not under your critical band. Okay, so this region will not be perceived by you, but this region will be masked up. Okay, but if let's say the sound or the noise from the bell is very soft, so my original the original critical band will remain unchanged, but perhaps you will still able to hear some noise, but at the background, something like that. So critical band is a band that you're able to hear, understand, perceive. Okay. So because the human auditory system, frequency dependence resolving power, the noise masking threshold is the noise masking threshold at any given frequency depends solely on the signal energy within a specific bandwidth neighborhood of the frequency. So this is what we call as frequency masking, whereby the masking is based on the frequency. So you have a very strong frequency or a strong tonal signal here. So this would be the region masked up by this specific strong frequency. Okay, which means if you have another frequency present, but the level of amplitude is very soft. So for all this red color line, you're not able to listen. But if let's say you have another frequency which is stronger than the masking region, so this uh, tonal signal or this signal will be able to be perceived. Okay. So in MPEG audio compression is performed by reducing perceptual and statistical redundancy. So all this region, all the data within this region, which is illustrated by the red color line, would be seen as redundancy because eventually they're present, they are not able to be perceived. So basically, in audio compressions, the MPEG is trying to search for this data and try to omit all this data. Okay. So basic task of the perceptual audio coding system is to compress the digital audio in a way that the compression is as high as possible because we always want to maximize the compression. The reconstructed or decoded audio sound is exactly as close as possible to the same to the original audio like before compression. So this is the two items that we want to maximize. The first one, we want to maximize compression. The second one, after we perform compression, we don't want to introduce any artifact or any noise into the original audio. So that is the two items that we want to maximize. So the range of human hearing is 20 hertz to 20 kilohertz, but some data may show 22 kilohertz. The sensitivity of the human ear decreased below and above the range of 505 kilohertz. Human hearing is insensitive to quiet frequency component to sound accompanying other stronger frequency component. This could be explained by the chart here. Okay, so this is the Fletcher Munson equal loudness response curve, which is also an empirical analysis. So basically, the mathematicians try to try to get a very big group of people and then play the audio at different frequency and analyze what is the sensitive regions of the auditory system. So as you can see this curve, this region, this is zero frequency, this is towards highest and infinity lah. Okay, and this is zero loudness, and this is very very loud lah, something like that. Okay, so but this curve is a bit weird. Is that the exit, the interval exit of the x exit that is different, which means this line is 1, this is 2k because it's kilohertz, because this is kilohertz, so this is 1, this is 2, 3, 4, 5, 6, 7, 8, 9, and 10. So the x exit interval is different. Sometimes we will have such kind of uh, chart lah. It's very rare we will use this type of chart, but uh, based on applications. Okay, so as you can observe, the chart here, the value would be higher. At this point, the chart would be higher, and at this point, the chart is higher. So the lower, which means, okay, maybe I put it like that. This is the y-axis is the loudness, which means here is 0, which means very, very quiet. Here is very, very loud. Okay, so very very loud. So which means we in norm if we are very sensitive to that particular frequency, we suppose able to listen to what people are talking in a soft loudness, which means at this part of this frequency, basically we are human beings are more sensitive. Why? Because you don't need to speak very loud, but people can listen to you. But in this frequency, you need to speak very loud so that someone nearby you able to listen to what you are talking about. And same goes to this area. Okay, so this is what the message behind this chart. I will explain later on further. We continue back here. So MPEG audio compression take advantage of this fact to reduce the extent and details of mostly or inaudible frequency range. So as based on the chart or the graph just now, we are trying to remove the data which is from very low frequency and very high frequency. That is because eventually the data is present, human being will not able to understand or perceive all those data. So we see those data as redundancy. Okay, so compression technology for audio signal that is based on imperfection of human ear. Perceptual encoding is lossy compression techniques. It is a lossy compression. Why? Because once we omit all those data, we are not able to recover. So that is called lossy. The decoded bit stream is not the exact copy of the original digital audio bit stream before the compression. So this reflects why it is lossy lah. Perceptual audio Perceptual audio coding is based on two related characteristics of the human ear. So the sensitivity of the human ear is not the same for all frequency. A loud tone or noise can make a weaker tone inaudible. This is so-called explained in the frequency masking. So if you have a loud tone here, so the rest of it will be automatic masked out. But of course, the masking is very depends from different people, and the sensitivity of ear is not the same for all frequency. If the sensitivity of ear is the same, so which means we don't have any redundancy in frequency lah. Okay. So irrelevant signal information is identified during signal analysis by incorporating several psychoacoustic principles into the coder. These principles include threshold inquired, critical band frequency analysis, and temporal massing. Okay, we will explain these three later on. These three would be the main items that how we actually determine this is actually redundancy information, etc. Okay, so-called the psychoacoustic. Acoustic is the energy in sound waves. We call it as acoustic energy. Psycho is that we try to perceive the human being, human perception, so-called the acoustic energy in human being. So we call it a psychoacoustic. You will find psychoacoustic in audio compression later on in this chapter. Okay. But I don't think we will explain in depth for psychoacoustic, because for psychoacoustic, I think there is three different types, and the model is very complex. So it is beyond our slippers. So basically, we will know what is psychoacoustic doing, but we will not focus in depth on what is psychoacoustic. Okay. So frequency less than 16 to 20 hertz or beyond 16 to 20 kilohertz are not perceived. So basically, all this frequency, all this data, or the signal within this range will be seen as redundancy. Amplitude below a given threshold are not perceived, such that the threshold depends on the frequency. So this is the curve that I mentioned just now. And the loudness is actually measured in fonts, or the unit is dB lah, but we call it as fonts. Okay. Okay. Look at this slide. Human auditory system is sensitive to frequency approximate 500 to 5 kilohertz. This range of frequency are then used to make the phone call. So that is why we will try to push the frequency of the uh, of any analog sound wave. When we listen to a phone call, the sound is a bit different, like a bit robotic to when you compare to the real person. So the reason is that the analog to digital converter is actually pushing the uh, input frequency towards this range, 500 to 5 kilohertz. So that is why, because the gap is quite small, and you are pushing all the frequency towards this band wave. So the voice or the tone will be a bit different, lah. Okay, so that is the reason why when you listen a phone call, the noise, the sound will be a bit different from the real person. This range of frequency are then used to make up the phone call, take the least energy for human auditory system to hear those frequency, which means if you have all the frequency in this range, you will be able to listen. Okay, easier for you to listen. So human auditory system is most sensitive to frequency around 3.5 kilohertz. So this is also the frequency of the what we call the guitar, the bass guitar, uh, electric guitar. Yeah, that is also the frequency of the electric guitar. So that is why when people playing the music, they are actually also trying to tune the music into this range. So it is, when some music being played, you would able to focus to different part of the music, and that is what the concert intended for. So although a concert is much more like a performance art, but nonetheless, there are a lot of engineering work over there. Okay, yeah. So human auditory system hear low frequency and high frequency poorly. How do we know poorly is that you need more, I mean, higher loudness to speak. So it's like, in library, you just need to whisper to your friend. But in a normal room, maybe you speak like normal, but in a construction area, maybe you need to speak louder and louder. So why you need to speak louder and louder? Because it's very difficult to heard or hear what you are talking about. So which means can you see this part and this part? The graph is literally going upward. So when the graph is going outward, which means you need more effort to produce louder voice or signal in order to perceive by another people. So this is what is reflected at here lah. Okay. So when the hearing reference level get louder, increase in dB, human hearing response flatten out. That is, hear all frequency range equally. The reference level of curve of loudness is 90 dB is almost flattened. Of course, when you look into this graph, it's not flattened at all because you have a wave like this one, right? Not flattened at all. But if you put this put all the interval in the x-axis in a same interval. I mean, the same interval, not like this one, a different interval. You will find that this curve is actually flattened out. But this one is still okay. But when you increasing from 10 to 90, you will find that this curve is flattened out to become something like that one. But the bottom one would have something still able to see the curve lah. Okay, so why it is flattened out is that the message behind this one is that when you are, I mean, generally the entire, if you are in a very loud environment, in a very noisy environment, no matter what frequency it is, still very difficult to understand. That's all. Okay. No matter you are inside the range of sensitive, which is 500 to 5K, or very low or very high, still very difficult to listen. Okay, because you are in very noisy conditions, which is 90 dB lah. Okay. Audio masking. Audio masking, we have two different types of audio masking, but just now we only mentioned frequency masking. We get to know about temporal masking. So frequency mask, actually I already mentioned the temporal masking. Frequency masking is that you are masked in terms of frequency. Temporal masking is that you are masked in terms of temporal, which means frequency masking, the x-axis is frequency. And when you have a very strong frequency, you mask out the adjacent frequency. Temporal masking is that when I mention temporal, always referring to time domain, okay, or space. So in this term, we are referring to time domain. So for example, you have 1, 2, 3, 4 seconds. A bomb happened here, okay. So within the next 2 seconds or maybe next 5 minutes, you will not able to listen anything. That is called masking. Do you understand the? Actually, both the masking is referring the same thing, lah. Not the same thing, lah. It's referring the same patterns over there. They are doing the same thing. Frequency masking is referring that you are masked by a specific frequency, a strong frequency. But for temporal, you are masking at a specific time taken. For example, at this moment, suddenly a bomb happened, so I cannot listen anything. Not because I die, it's because the humming issue. So the next 5 seconds or next 5 minutes, I will not able to listen anything. So that is so-called the temporal. But at the same time, when the bomb happened, the frequency is very strong. So I will suffer from both the frequency and temporal masking. Do you understand? So this is the difference between frequency masking and temporal masking, because we are talking in different perspective. So you have different kind of masking, okay? And sometimes temporal masking may present, but the specific frequency for us for that particular temporal masking may not be strong enough. So we will not mask the rest of the frequency, okay? So we have two different types of masking here, which is masking is referred to the process where one sound is rendered inaudible because of the presence of another sound. It is used to investigate the frequency selectivity. So you have two masking, frequency and temporal. So frequency masking. Threshold of hearing is the absolute threshold of hearing characterized the amount of energy needed in a pure tones, such that it can be detected by a listener in a noiseless environment. The frequency domain phenomenon where a low-level signal, the musky, can be inaudible. Musky is the one that being masked by someone else. We call it as musky. Masker is the one who masks someone. Okay, we say masker is the bully lah. So musky is the one being bullied lah. Okay, can be inaudible by a simultaneously occurring stronger signal, the masker. The masker and musky should be close enough in frequency. Because eventually, if you have a masker here, you know, uh, the masking, frequency masking will be somewhere around here. But if, let's say, after the frequency masking range, you have a very, very soft frequency. But because this frequency is beyond this range, this frequency is still able to be perceived. Okay, because the idea is that the masker and masking must be very close together lah. If not, we will not being affected by this mask region. Okay. The masking threshold in the context of source coding, also known as threshold of just noticeable distortion, varies with time. It depends on three items: the sound pressure level, the frequency of masker, the characteristic of masker and masking. These are the three items which will affect the masking threshold. So let me see. Okay, you have a strong frequency here. So this would be the region masked. This would be the region masked by the. This would be the region masked by the frequency masking lah. Okay. So you have a signal here or tone here, because the dB or the loudness is lower. Within the masking envelope. So it will being masked out lah. Okay. So we so call this one as masker and this one as masking. Okay. But for this tone, we were able to perceive is because the frequency is higher than the masking envelope. Okay. So that is the idea lah. Okay, and this is another region whereby you need to slowly recover. Effect of threshold of human hearing for 1 kilohertz masking tone. Effect of masking tone of 3 different frequency. Let me see. Okay. What is means by what is the message reflect by this chart is that if your frequency is higher, you need a longer time to recover. For example, if someone just yell just beside your ear, you might suffer from a very short humming period. But later on, but when you compare this humming period to a bomb happen just nearby to you, for sure you will need longer time to recover. That is the difference. Because as you can see, for the frequency in 8 frequency, I mean 8 kilohertz, you need a longer time because the envelope, flattened out. You need a longer time. But for this one, you only need a shorter time to recover. Okay, and for 4K, you need sort of this one. But of course, I cannot say that this chart is applicable to everyone because again, uh, auditory system is very subjective because my capability to listen something else is would be different from what you can listen. Maybe I'm not so sensitive in hearing, but you may be very sensitive in hearing. So the curve would be different a bit lah. Okay, but nonetheless, this would be the theory behind that. The higher the frequency, the wider the masking effect would be. Okay, so critical band is what I mentioned just now, which is the band that you're able to listen for a specific signal or tone. So the human hearing range naturally divide into critical band with the property that the human auditory system cannot resolve sound better than within about one critical band when other sounds are present. Hearing has a limit frequency dependent resolution. Um, this is what defined by the Fletcher Munson curve as well. Because when we are more sensitive at the range of 500 to 5 kilohertz. Beyond this range, we still able to listen, but you need to speak in with a louder voice and etc. Okay, but beyond, I mean, lower than 16 uh, hertz or beyond 20 kilohertz is hardly for ones to listen because that is beyond the capability of human auditory system. At the low frequency end, a critical band is less than 100 hertz wide, while for high frequency, the width can be greater than 4 kilohertz. This indeed is yet another kind of perceptual non-uniformity, which means the critical band is the area where one human can listen to a specific sound. Okay, so in low frequency, the critical band is less than 100 hertz, which is very small. But in high frequency, the width of the critical band can greater than 4K, which means we not able to listen when we, I mean, when in low frequency environment or the input analog signal is very low, it is in low frequency, our critical band, the band area that we can listen is very small. But when the frequency is higher, uh, I mean, towards the right hand side with higher frequency, this is low frequency. The critical band would be higher. Okay, the critical band gap would be greater, which means, for example, this is 100 hertz. This is 4 kilohertz. Okay, so experiment would be the Fletcher Munson indicate that the critical bandwidth remain approximately constant in width for masking frequency below 500 hertz and above, which is about 100 hertz. Okay. However, for frequency above 500 hertz, the critical bandwidth increase approximately linearly with frequency, which means uh, you increase by one, I increase by one. This is called so-called linearly. Or not really directly proportional, but something in linear. Okay, which means you increase, I increase, but the factor of increasing might be different. So generally, the audio frequency range for hearing can be partitioned into about 24 critical band, 25 typically used for coding application. So which means a human, a normal human, the hearing capability will be around this 24 critical band. If let's say you have 24 critical band, you can see this as a band gap. If the if a signal is beyond this band gap between 4 at this area, you will not able to listen, something like that. Okay, you can see this the full range of human being can listen would be 24 band gap. 24 band gap. Okay, if a particular signal fall out from this particular band gap, for example, this is the band gap, and if you have a signal fall, I mean beyond this band gap or interval in this band gap, so we will not be able to listen. So for those signal within the band gap, we'll be able to listen. Okay. And if another noise come in and interfere your specific band gap, so we'll mask out this one. You'll mask up your original band gap. Original critical band. So when the original critical being masked out, there are two conditions: frequency masking or temporal masking. So this would be the ideal lah. Okay. In general, definition of critical band, our hearing apparatus actually is somewhat tuned to certain critical band. So for those that are using the hearing system to add on the hearing capability, actually you are going the device is actually collecting the analog sound wave and put it in the specific band gap and trigger directly to our depends on what is the level lah. Some will be triggered to because some might be insensitive to hearing but not completely deaf lah. Completely deaf the device will be different. But those that are not so sensitive, the doctor will first determine what would be the critical band gap you have, and then fine tune it, and then from there, the device will collect the sound wave from the ambient environment, and then push that towards your critical band gap so that you can listen. Okay, so this is the idea in audio processing. Okay, I think today we'll stop here first, and we will continue later on. Okay, any questions? So today we do not have tutorial. And yeah, see you all next Tuesday. Thank you.